check, check.
Hello, hello. Good evening, ladies and gentlemen.
The hall is full, and the reason you all know. Professor Stephen Hell is here on the stage. I request Professor Vijayalakshmi Saxena to come on stage, and I also request Professor K.S. Rangappa, both of them, they happen to be chair and co-chair, to accompany the Nobel laureate on stage, please. Professor Vijayalakshmi Saxena. After the inauguration of the 107th Indian Science Congress at the University of Agricultural Sciences by the Honorable Prime Minister of India, we have gathered here in this iconic International Convention Center for the first public lecture by Professor Stephen Hell, the Chemistry Nobel Laureate for 2014. Professor K.S. Rangappa will introduce Professor Hell a little later. I will quickly introduce both Professor Rangappa and Professor Vijayalakshmi Saxena. This session is being chaired by Professor K.S. Rangappa, the General President of the Indian Science Congress Association. He has 475 publications, 10 patents, over 7,500 citations with the H index of 43 to his credit. He has successfully guided 55 PhD students for their doctoral degree. He had invited 11 Nobel laureates to the University of Mysore during its centenary celebrations in 2015 and 16, and he created a benchmark, hosting the 103rd Indian Science Congress at the University of Mysore. Professor Rangappa is a recipient of many prestigious awards. I welcome him on the stage. Professor Vijayalakshmi Saxena, who is co-chairing the session, is the president-elect of 2021. She is basically a zoologist and has 45 years of research experience. She is the coordinator, Bioinformatics Infrastructure Facility Center of DBT, Government of India. She is the coordinator, Central Institute Body, Standing Academic Committee, Standing Hospital Affairs of the All India Institute of Medical Sciences, New Delhi. Professor Saxena is the member of Academic Council, KIIT Bhubaneswar. She is also the former member of Academic Council, University of Mysore. She is a recipient of many prestigious awards. Now, I request Professor K.S. Rangappa, the chair of this session, to introduce the Nobel laureate.
Good afternoon, everyone. It's my privilege to introduce Professor Stephen Hell for the first public lecture. Professor Stephen Hell, the honorary FRMS, is a German physicist and one of the directors of the Max Planck Institute for Physical Chemistry in Göttingen, Germany. He received the Nobel Prize in Chemistry in 2014, the development of super-resolved fluorescence microscopy, together with Eric Betts and William Moiner. Stephen Hell received his doctorate in physics from the University of Heidelberg in 1990, followed by a research stay at the European Molecular Biology Laboratory in Heidelberg. Stephen Hell holds honorary doctorates from the universities in Finland, Romania, Sweden, United Kingdom, and Switzerland. He was selected as lifetime member of the Optical Society of America in 2014 and appointed as honorary member by the European Physical Society in the same year. Since 2015, he is also honorary member of the German Bunsen Society for Physical Chemistry. He received the Order of Merit of the State of Baden-Württemberg in 2015 and the Federal Cross of Merit in 2016. Professor Stephen Hell's discovery in the area of fluorescence microscopy, which everyone knows. Again, I am privileged to introduce Professor Stephen Hell, Now to Stephen Hell.
It's a great pleasure and great honor to be here and to speak about the science that I've been developing over the years with my team. Can I have the first slide, Gopi? So I'm sure you're familiar with the saying that pictures worth 1,000 words of seeing and feeling, and this is not only applies to our daily lives, it also is true for science. Because at the time in my master's was in history, actually natural science evolved. Because with the microscope, people were able to see for the first time that every being consists of cells and basic units of structure and function with the light microscope material discovered, and of course many other things, such as the lower and mitochondria. But I'm sure you remember the school days when we were told that the resolution of a light microscope is fundamentally limited by diffraction by wavelength of light to about 200 nanometers. And this is the reason why electron microscopy was invented. And the electron microscope has a reason that it didn't use focused light, but electron needs a much higher spatial resolution. Resolution could increase down to the size of an atom or even subatomic scales nowadays. And there's plenty more discoveries that are going such as viruses are discovered, and of course many things in the cell, and so on, those are material sciences. And therefore, the physicists, of course, make a lot of sense to us to really upholding looking at light microscopy and the resolution of light microscopy. And actually, what I did as a scientist, of course, I looked into the case of whether the light microscope can have a higher resolution, but it's really a way to get much higher spatial resolution. And the motivation for that, of course, is very easy to explain. With an electron microscope, you can see only that material. It's not possible to look into a living cell and see, for example, the physiology going on in the cell. Moreover, we know nowadays that there are nucleus in the cell, there are all kinds of organelles in the cells, so there's not much to be discovered. But what is still unknown as of now is, for example, where are specific proteins located during the cell cycle, or what do they do, how do they interact with each other? How does the change of the protein distribution evolve over time during the cell cycle? So we want to know what is actually going on. And this cannot be done with an electron microscope because in electrons it's very hard to identify proteins specifically. Now that's the strength of light microscopy, because in light microscopy you have the option of fluorescent labeling, meaning that you can attach a fluorescent molecule to the protein of interest. And then, of course, you don't see the protein of interest, you're going to see the fluorescent molecule that indicates the protein of interest, because the labeling of that protein can be done with extremely high specificity. So the phosphor goes only to the protein of interest. And so, this version of light microscopy, which is called fluorescence microscopy, where you use a phosphor that is attached to a protein, has become very popular. So 80% of the cases in the life sciences, when they resort to a microscope, they resort to fluorescence microscopy. And therefore, it makes a lot of sense to realize the resolution at class to really know light microscope or specifically a fluorescence microscope that can have a higher resolution than what we showed you that goes beyond the diffraction area. Now, I'm telling you now that my motivation was to make a light microscope or fluorescence microscope that has a higher resolution. I'm not like telling you the truth. As a matter of fact, I've been showing this slide for 2 decades or so, and my only motivation to show this slide was to get funding. The real motivation for me was, next slide please, to find out if I can crack this area, if I can do something that next slide will be, that really makes things, that makes this problem go away. And therefore, in this slide, I'm showing you what the actual problem is. things revolutionary in very simple terms. Now, the most important element of the light microscope is the lens. It's also a objective lens. You see the lens in blue, and you see a sketch of some which consists of molecules as well. Now, nowadays, what we do is we use a light source, which is a laser, as you can see here, and the goal of the lens is to focus the light source down to a point. Now, if the lens could focus the light down to a point, of course, a real point, then you could address a single molecule, and each molecule individually. However, that's not really possible because negative light propagates at waves, negative, and therefore the light produces a lot of light in the photorevolution example, it will see it out, and that's due to the wavelengths. Negative, and you will see that, say, the diameter, the radial diameter of the light is about 2 nanometers. And this is where the revolution problem comes from. Because what will happen, negative, all the molecules that are within this range of light, this block of light, will be different at the same time, and these fluorescent molecules will fluoresce at the same time, as you can see here from the sketch, they will glow yellow, and then negative, what will happen, they will also produce light, which is then collected by the lens, goes negative to the detector, and because this light is also propagating as a wave, we will have a lot of light also under the detection plane, and each of the molecules negative will produce a lot of light and they will overlap in space. Why do they overlap in space? Because they are supposed to gather in a green spot. And therefore, negative, no matter what detector we create, could be the eye or even the camera, it's not possible really to tell the signal from these molecules apart. So there's no way for a detector to tell the signal from these molecules apart. So, this is one problem. So, this is the most profound way of explaining this resolution problem in the light microscope. Next thing. Now, the person who realized this problem was this man, and who lived at the end of the 19th century in Germany, and he formulated this diffraction resolution problem as in the equation that is named after him. It's called the right-hand upper corner. It's basically saying that the main resistance that can be served in the light is produced by the wavelength lambda divided by the number of the denominator, which is called the numeric aperture. That's a number like 2 or 3, and therefore we give the wavelength you are interested in this type of philosophy, you want to know about science, okay? And I know you cannot know about science. But we should know, of course, that every scientist has lived a life. And in my case, of course, the science that I've done is tightly linked with my personal life story. So I'm going to tell you about my life. Next week. So I was born in a small town, actually, in a village in the east of Europe, what is now Romania, West Romania. And this was a communist country, and living was not so good. And at the age of 13, I could leave my parents. I was an only child. That's where trying to get out of the country, if that's possible, was very hard because it's too hard to in those days. Let's get out of the country and move towards Germany, that's possible. And after some struggle, when I was 14, 15, we managed to get out of the country. Between 83 and actually 1990. But the thing was the following. Of course, most physicists at that time at least, and I'm sure there are many young students around here who study physics, and I was interested, of course, in doing basic things, fundamental things. I want to maybe become an astrophysicist or doing something fundamental with unifying the forces. I want to become a theorist. I want to do something fundamentally profound. But at the time, I had to make a decision on which PhD subject to choose. I spoke to other students who studied physics who were more advanced than me, and said, you should not do that. If you do that, you may easily end up unemployed. And you may end up as a taxi driver or something. You should. And so it was still light microscope, which was, let's face it, it was the physics of the 19th century. There was nothing special about a light microscope. Physicists had discarded microscopy. This is not physics anymore. This is just technology. So I was very frustrated, as a matter of fact. I was close to becoming depressed because I'm wasting my life. I'm doing something wrong. And then, of course, I had two choices, either to become miserable, or the second thing is, well, if I have to do this kind of nonsense and this, say, low-level science, maybe there's still something interesting, an interesting problem that is left that could be fundamental. Maybe there's a fundamental problem left in microscopy, and that is, of course, breaking the diffraction barrier. That would be cool, because everyone thinks it's not possible to get a light microscope that has a higher spatial resolution. So I realized breaking the diffraction barrier, that would be worthwhile working on. So that's the only problem that is left, and it is really, really cool and really interesting. And this is how I got to think about the problem. And this was a totally crazy idea. I mean, because textbooks saying it doesn't work. I mean, there's no way of doing it. I mean, everyone believed that. And you start out with saying, okay, let's do this kind of thing. But at some point, I became convinced that this would be possible. Why? My thinking was the following. The diffraction barrier was found by that man, Abbe, at the end of the 19th century, 1873. And this was in 1988 or so. And so 100 years had passed in the interim. So within those 100 years, so many new phenomena were found in physics, in chemistry. There must be something that gets you beyond the diffraction barrier. So I said, okay, I just have to open my textbook and look at all the physics that was invented after 1873, and hopefully there is something that gets me beyond the diffraction barrier. There is a phenomenon that gets me beyond that. And this was my strategy. I screened textbooks, hoping to find the phenomenon that gets me beyond the diffraction barrier. And then, of course, I tried to convince my professor. Said, oh, this is too crazy, it's not my field, and so on. I wanted to stay actually in Heidelberg, but I couldn't continue. At some point, I even was unemployed for 3 months and worked on my own somehow. But then I was lucky that I met a person from Finland, that's the northern part of Europe, in a place I'd never heard of, called Turku. I'm sure most of you will not have heard of this place as well. And the person there said, okay, you can come to my lab, you have to arrange for a fellowship or so, but you can think about this crazy diffraction barrier thing. At least I had a place where to be and to start my work. And next slide. And believe it or not, 8 weeks after I got there, I got the idea that actually, in the end, won me the Nobel Prize. And so, next slide. And now I'm explaining this idea to you. In retrospect, of course, it's very simple. You remember the problem. We have the lens, we have the laser, we have the blob of light, we have, of course, all the molecules. Technically speaking, what happens is the molecules absorb a green photon, they get to the excited state, and then they glow light, and then, of course, they produce light at the detector, and since there are so many, it will be confused. And what I had realized in that very moment was that not only can the molecules make glow with light, which is actually what happens normally. You see you have the green light and then the molecules glow, and then you get light here at the detector, which you detect, but you can also make the molecules dark. For that, you have to use a certain wavelength of light, a specific wavelength of light that can be made the molecules not glow. Just turn them off. You can turn them off, and then they don't glow despite the fact that they are covered by the green light. The only thing you have to do, you have to choose the right wavelengths. And if you choose the right wavelengths, of course, then you can make the molecules go from the bright state, from the excited state down to the ground state without emission of a fluorescent photon. You essentially turn them dark. And now you can imagine what I wanted to do. I wanted not to turn off all the molecules, that wouldn't make much sense, but to turn off many of them, but one or a few that are, say, here in the middle of the spot. And this is exactly what I did. I changed the shape of the red beam such that it looked like a donut or a ring and had a hole in the center. And then this beam turned the molecules off, and only the molecule in the middle was able to glow. And so you imagine this was a fundamental idea, because then not this problem that is here, of course, is sorted out, because there's only one molecule that is glowing, for example, and then, of course, you can separate that molecule from the rest. And this was next slide, idea called STAT. Just go back. Next slide, and okay. And this was published in '94 in a theoretical paper in a journal called Optics Letters, very low impact factor, 2 or 1.8 at that time. I didn't dare to go into a big journal, and it was just a theory. And I was totally unknown at that time, so no one would have thought. And now I was very naive about science. I said, okay, if you have a good idea, and I presented this idea at meetings, and of course I published it in a paper, I thought, okay, now the established science would clap and say, great, just as you did. You had a good idea, and now you should get some money and the lab perhaps, or space in the lab to do the work and to prove that is right. But this did not happen. This did not happen. Next slide. Actually, it was very, very difficult to survive scientifically here in this time. Next slide. Because no one believed in it. They said, oh, why should this guy from Finland we have never heard of have a profound idea? None of the ideas that others tried worked, so nobody believed in it. So I went from meeting to meeting. I paid the meetings out of my own pocket. I couldn't have savings. He was a very poor guy. I lived in a very small, in a student village, actually. Really, I couldn't have invited you there, honestly. And so it was very, 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 very sad circumstance. Just couldn't, without savings, just like that, couple of years. But, so it was difficult to survive. At some point, I filed a patent, then I sold the patent to a company. The company gave me money in return so that I could continue. But the point I'm making here, next slide, honestly, although it was objectively a very hard time for me, I was much happier during that time than during my PhD. Why? Because I worked on a fascinating problem. I worked on a problem that I really wanted to work on. There was no one else working on this resolution problem. I was the only one. There was no competition. It was just me. And that, of course, it was much more satisfying. I was poor. I didn't have a real job, so it just fellowships that went on for 6 months or 8 months or 4 months and so on. But I worked on a fascinating problem. This was very, very gratifying. It went on like this for about 3.5 years in Finland, but of course you cannot go on like this forever. Next slide. And so I was lucky that I got introduced to a scientist who worked at the Max Planck Institute in Göttingen, where I am now. And next slide. And they said, oh, this is an interesting guy with an interesting idea. We don't think he is right, but at least we give him the chance to prove that he's right or disprove, because he's the only one who works on the resolution, and if you don't allow him to work on this, we will never know. So they gave me a 5-year contract, which was heaven for me, 5-year contract, for the first time a real contract, to work and some lab space to work on proving my theory, if I can get sharper pictures. But the thing is, I didn't ask for enough money to make my experiment. Because a poor guy, I was very modest, I didn't ask for enough money. And then I applied to the German government, sent an application, sent it in, hoping that it would get a grant. And then what I got was a rejection. And there were 12 experts in a panel, and these 12 experts say, this is not serious science, this is not going to work, this is not done professionally, this theoretical proposal is not right, and you should not give the grant to this guy. And then I complained to the officer at the agency, at the ministry agency, and then the officer said, okay, well, at least it's an original idea. You tell us the reason why all these 12 experts are wrong, and if you have convincing reasons, we give you the money. And so I wrote 2 pages overnight and sent it in, and they gave me the money, and I could do the experiment. And believe me or not, this experiment, which was done with this money from the rejected grant, was the experiment that was cited by the Nobel Commission at the time I won the Nobel Prize. And it worked. It worked. So this before and after, and you can see that it was clear with this experiment that you can overcome the diffraction barrier and you can get a higher spatial resolution. And this is here demonstrated with these colloids. And of course you get it also in a cell. So this is now the standard resolution, and this is now the, say, sub-diffraction resolution STAT microscopy, where it shows this is a nuclear pore complex. This is what this protein is called, that you can get a higher spatial resolution. Go ahead. And you see here, I'm zooming in. So you see quite nicely the 8-fold symmetry. And if you compare it with standard confocal, you see nothing. I still like making this comparison, although it's textbook knowledge. You find it in textbook, these pictures. But it's just showing you that this really has happened. Move on. And of course, it can be used to see details like the cristae in the mitochondria. Just move on. In living cells, just, okay. You see here, these are dividing mitochondria. Move on. And it's actually quite nice to see the cristae and this division, of course. And actually, I'm not a biologist, so I'm not really interested in the applications. I'm just a physicist who wanted to solve a problem, a diffraction resolution problem. And so this is just to give you an idea of what you can do with a higher spatial resolution that really made a difference. So let's move on. The point I'm making here is At the time, the first experiments were made, where I worked in the lab, and this was a student that joined me later. It looked all very complicated. Yeah, you see, it's very complicated. But now, it's something that is commercially available. Actually, here at NCBS, there is such an instrument, such a STED microscope, by the way. Move on. Meanwhile, it's so small that you can put it even into a shoebox that fits onto any microscope stand, and move on. And the picture, this picture that you've seen initially actually, was taken actually with such a commercial system with a company that was set up by my students and myself, startup company. And this picture made it on the official poster of the 2014 Nobel Prize in Chemistry, which shows actually the concept of STED microscopy. You will recognize the beam for turning on, the beam for turning off, and of course the fact that you have just signal from here from the center, and then hence a higher spatial resolution. And move on, please. You see that I shared the Nobel Prize, as Professor Rangappa mentioned in the beginning, with two American colleagues who came up with a similar concept 6 years later, which has advantages and disadvantages, of course, and it also works by playing on and off with the molecules. But in this case, the molecules were turned on and off on an individual basis. So just one molecule was turned on and the rest in the neighborhood was off. And this concept, it has the name palm or storm, became also very effective. And therefore, I had the honor of sharing the prize with these two gentlemen. Okay, move on. Now, actually, these are the two, say, canonical methods that are now being used for imaging at high spatial resolution, and such a system is also at NCBS, by the way. Now, this was in 2014. So these two concepts existed, and they were given the Nobel Prize too. Okay, now, believe it or not, both concepts can have a spatial resolution that is really at the size of a molecule. So not 200 nanometers, which is the diffraction barrier, and going down to 20, as you've seen, but to 2 nanometers is possible, in theory. But at the time the Nobel Prize was given, believe it or not, at the time the Nobel Prize was given, in 2014, none of these concepts could provide a spatial resolution that was really better than 20 nanometers. It was a factor of 10, which is great, no doubt. But they could not reach the ultimate limit, say, of 2 nanometers or so. What's not possible. For example, molecules that were arrayed like this, you see the dots here in this cartoon, they could not be resolved at that time, 2014. Just click. I'm showing you here such a recording with this concept on the right-hand side, and you see it's not resolved. So what I did is, I said, okay, let's come up with something new based on the strengths of each of these techniques, and maybe we can improve the resolution even further. So that was work that was done after the Nobel Prize. You see, it came out in Science in 2017. And it's called MinFlux. And the idea behind MinFlux is to combine the strengths of the two techniques. The strengths here of this technique on the right-hand side is that you can turn on the molecules individually, so you can make the separation on the individual molecule level. And the strength of this technique is that you know where the molecule is if you match the hole with the molecule. So you see there's a beam with a hole, but this time it's not red, it's green. And if you match the hole, so to speak, of the beam with the molecule, then you know where it is. And so the combination of these two led to this concept, MinFlux, which is a new thing. And now just click. You will see, just do the next click, please. You will see that we can tell the molecules apart. Now the resolution is really down to the size of the molecule. You see the distances here. So we're talking here about resolution of 1, 2, 3 nanometers. So it's a factor of 100. So the Nobel Prize was given for increase of resolution by a factor of 10. And now, after the Nobel Prize, my group is by a factor of 100 improvement. And this is, again, a substantial step. Now I'm going to show you examples. Yeah? So this is now a recording with this new concept, MinFlux, again from these nuclear pores. Just click on them, and then zoomed in. you see that the resolution is even better than before, okay? And this is the technique that won the Nobel Prize, and this is what we can do now. And the old technique, just click one more, is this. No comparison. So I really feel sorry if you still have to use the old technique. There is something that is happening, and you should really look into getting higher spatial resolution. Now, you can do this, just click also in living cells. So this is now taken from living cells, these nuclear pores. And just move on. And also in 3 dimensions and in multicolors. So this is again, if you can go back, go back, yeah. Go back and then click on again. So you see 2 color recording, and just click on it again. And a 3-dimensional, say, rendition of this nuclear pore. So you can relate proteins to each other. And this is, of course, very exciting. So this is cutting-edge new science. So this just came out in Nature Methods this month. And so what I'm saying by this is you can have in the cell now a spatial resolution that is of the order of the size of the molecule, say 2-3 nanometers in 3D, and also in living cells, and in multicolor. And this is just the beginning. And of course, there will be many applications. Next slide. You can imagine, for example, imaging proteins in 3 dimensions in a cell with a resolution no one would have anticipated even 10 years back. I would say 10 years back, or if somebody had said, oh, at some point we will be able to image distribution of proteins with say, true molecular resolution, say, crazy, nuts, this will never work. With a light microscope that just uses objective lenses, but it's possible. And there's many applications coming up in this field. And so I'm very confident, since most of you are not interested in microscopy, what will this bring about? It will teach us how cells work at a fundamental level. And you don't forget, every disease, no matter what it is, infection, cancer, whatever, a neurodegenerative disease, in the end, it's a malfunctioning of the cell. And once we understand how cells work, how the proteins are arranged, what they do, we also understand the malfunction. And I believe that in the end, the fact that we can see better over the coming years will help us tremendously to understand diseases and hence also to find remedies or to counteract them or to even heal them. So with that, next slide. So you can imagine, just keep on clicking. One can imagine looking into all kinds of things, like looking at synapses, vesicles, the nucleus, looking at molecular dynamics, but you're welcome to imagine your own applications. If you're in the life sciences, plant biology, say neurosciences, cell biology, whatever, developmental biology, there's definitely more to come. Next slide. So I'm acknowledging the people who actually did the work in the last part of the experiment, so really worked hard in the lab. So these are very, very talented students. I don't have a big group, so I like to work with dedicated people. Next slide. And of course, this is the equation that you've seen. The thing is, of course, it cannot describe everything now. There is more to it. It can be modified just to accommodate the fact that you can have a spatial resolution that truly goes down to the molecular scale. And so we know now you can have indeed a spatial resolution that goes down to the molecular scale. And so finally, I would like to well, at least for a younger community, sum up by telling you about the lessons that I learned in this context. Click on the slide. First of all, you shouldn't think that consensus is reality. And also in science. There could be consensus on something, but sometimes people are blind, and sometimes all of them are blind. It is like that. So consensus not necessarily matches reality. Click on next. Then challenging consensus. If you challenge consensus, this is not always welcome. So when I came up with the idea that there should be a way to get a higher resolution light microscope, of course the electron microscopists hated me. Say, oh, no way. Don't take science money for that. It should be given to electron microscopy, not to you, because this is not going to work. This is just baloney, and you're not serious. And also the normal light microscopes hated it because they did other types of microscopy, and they didn't want me to succeed because I put them out of business. It was very logical. And so, of course, challenging consensus, that is something that is not always welcome. I was very naive as a young man. I really thought that if you have a challenging idea and you put up a new idea, then the world would welcome you. This is not the case. Again, the next one. So fundamental advancements, in my view, usually are very simple. So if you ask me what is the gist of the whole discovery, the gist of the discovery is that you make sure that you turn molecules on and off. So if you have two molecules that are too close, you make sure that this one is off and not producing the yellow light when this one is, and if you turn this one off, this one is emitting. And so by making sure that they do not emit at the same time, basically, that you play on and off with them, you can tell them apart. So in the past, people thought you have to do the separation by the focusing of light. And this was a misconception for about 120 years. But once you realize that you play on and off, you can play on and off and do the separation by on and off, then the diffraction barrier and the resolution problem is gone. Next one, and this is my final slide. So very often people ask me for a motto. So what would you recommend us? So what should be our mindset to be successful? And this is what it is. Aim high, stay grounded. And if you're lucky and have a good idea, you might even win a Nobel. Thank you very much. Thank you.
It's fantastic.
Thanks. Thanks.
Nobody could beat this kind of acting.
Thanks. So what's happening now?
Wonderful job.
Yeah. Thanks. Thanks, please.
Nice, very elegant.
Thought-provoking, really, everybody can think.
Okay. Are there questions or what is?
No questions. I don't take questions.
So why are we sitting?
Not allowed. Only the felicitation for you.
Sorry?
Felicitation.
Oh, okay.
Extremely sorry for the confusion. Now I request Professor K.S. Rangappa, the chair, to present the memento to the Nobel laureate who has delivered a great lecture this afternoon.
So this is.
Thank you.
I request Professor Gangadhar to present a memento to the chair, Professor K.S. Rangappa. Professor Gangadhar is giving a memento to the chair. Again, I request Professor Gangadhar to present the memento to co-chair, Professor Vijay Lakshmi Saxena.
It's very nice. No, we better to ship it.
Yeah, okay.
Yeah.
We will do that.
Yeah.
Thank you, sir. I request Professor Vijay Lakshmi Saxena to sum up and propose a vote of thanks.
Probably ship it from here.
Yeah.
We are grateful to Professor Hell, who came a long way from Germany to 107th Indian Science Congress. We really appreciate your very good work you have done, the work you have done really, and it is thought-provoking for all of us. Let's appreciate Professor Hell, the Nobel laureate, for his illuminating talk. And he has enriched us in different aspects of microscopy, nanoscale resolution, and mind flux nanoscopy. I am also thankful to Professor Rangappa and all the council members, all the staff sitting here, all the students and participants. Thank you all.
Just a moment. Tomorrow evening at 6:30, after all the deliberations, sessions, there'll be a cultural program in the same venue where we had the inaugural program today. Tomorrow, Prabhat Kalavidru will present Cinderella, a ballet. The story of Cinderella, most of you know, the poor girl, the angel comes and helps her. That story will be in the form of a ballet tomorrow evening. And on Sunday evening at 6:30, two famous musicians, one Vijay Prakash of Jai Ho fame and Praveen Godkindi, a Bansuri man, the two will present a Jugalbandi, fusion music Jugalbandi on Sunday in the same venue, the main pendal. And on Monday evening, Prabhat Kalavidru will present a dance drama.
Ladies and gentlemen, kindly assemble again at 4 o'clock for the second public lecture. The second public lecture is at 4 o'clock. If you feel comfortable sitting where you are, feel free. Otherwise, if you want to take a stroll, please feel free. ಈಗ ರೆಡಿ